Hello friends, in the diagram video series of class 12 physics, today we are going to learn to draw the diagrams of the chapter magnetic effect of current and magnetism. Okay, so let us begin with the first important diagram that is most of the times is repeated in the board exams. That is the diagram of finding the magnetic field at any point on the axis of current carrying circular coil. Magnetic field at any point on the axis of current carrying circular coil. Diagram of finding magnetic field at any point on the axis of current carrying circular coil. So let us begin. This is the circular coil and it is carrying current I, suppose in anti-clockwise direction, and the radius of this coil is suppose capital R, and this is the center of the coil and you want to find out the magnetic field at any point P. Suppose this is the point P at which you want to find out the magnetic field of this current carrying circular coil using Biot-Savart law. Okay, so suppose this point P is at a distance x from the center of the coil. So to find the magnetic field at this point, what you do, you cut a small current element from the top of the coil. Suppose this current element is IDL and you join it to point P, and this distance can be taken as R, and now we find the magnetic field at this point, and the magnetic field at this point should be perpendicular to both IDL and R. You know from Biot-Savart law, dB is proportional to IDL cross R. So that means it should be perpendicular to IDL. Magnetic field should be perpendicular to current as well as it should be perpendicular to R. So this magnetic field dB1, you can call it dB1. It should be perpendicular to this R vector. It should be perpendicular to R. इसको dB1 को इसके perpendicular होना चाहिए. तो यहाँ पे हम ये दिखाएंगे, देख सकते हैं आप, ये perpendicular दिखाना है इसके. So now what you do, you just resolve it into two components, dB1. So this component and this component. Now let us suppose this angle is, you can take any angle alpha, and if it is alpha and this angle plus this is 90 and this plus this is also 90, so this is also alpha. This is also alpha. So this component is dB1 cos alpha and this component is dB1 sin alpha. The same thing you can do, you can cut another current element from this lower part of this ring and you can join it to point P. You can join this current element also to point P, and you can find the magnetic field in the same manner. Suppose it is dB2 and that dB2 will be perpendicular to, again this is also R. तो इसको हम दिखाएंगे नीचे की तरफ ऐसे करके, और ये dB2 भी परपेंडिकुलर होना चाहिए आगे, इस वाली आगे. तो this is alpha. So because this triangle and this triangle are congruent, so this angle is also alpha. And if this angle is also alpha, so you can now make two components of dB2, this component and this component. And this is alpha, so this angle will also be alpha, and this component will be dB2 cos alpha, and this is dB2 sin alpha. Now this your diagram is ready to find the magnetic field at any point P on the axis of current carrying circular coil, and from there you can see that cos alpha components being equal and opposite so they will cancel out, and sin alpha components they will add up because they are in the same direction. Okay, so this is your diagram to find the magnetic field at any point on the axis of current carrying circular coil using Biot-Savart law. Okay, so let us draw another diagram. The next diagram is diagram of the important diagram from this unit is diagram of cyclotron. Okay, so you know what is cyclotron. So let us start to draw the diagram of cyclotron. So you know cyclotron, what is cyclotron? Cyclotron is a device which is used to accelerate positively charged particles. Cyclotron. So for this we will draw schematic diagram. Schematic diagram. In your exam, only schematic diagram of cyclotron is asked. So to draw this diagram, first of all, we will draw a uniform inward magnetic field. Suppose this cross represents uniform inward magnetic field. And because you can see that the cross are placed at equal distances, there is equal gap between these crosses, so the magnetic field is uniform. Now the cyclotron consists of two D-shaped hollow metallic conductors. There are two D-shaped hollow metallic conductors you will draw here. This is suppose D1 and another conductor that is called D2. This is D2. This is D1 and this is called D2. Now these two Ds are connected to a high frequency oscillator. This is high frequency oscillator which continuously changes the polarity of Ds. Now to accelerate, and there is a gap, you can see here this gap. This is the gap. Through this gap, charge particle will emerge out after being accelerated. Once the charge particle is accelerated suitably, once the charge particle is accelerated to suitable high speed, it can be taken out using from this gap. Charge particle comes out through this gap. Now to accelerate a charge particle, what we do? We place it in the gap between the two Ds here at the center of Ds. This is the positively charged particle that we want to accelerate, and as you place it inside between the gap between the two Ds, this charge particle gets accelerated and it moves like this. It goes like this, like this. So radius of the charge particle, circular path goes on increasing, and when the radius of Ds becomes sufficiently high, that is equal to radius of D. So this charge particle comes out through this gap using deflecting plates and it can hit the target. So this is your diagram which is ready, the diagram of schematic diagram of cyclotron. This is very important topic, so please practice it again and again. Now we will draw the next diagram to find the force per unit length between two straight parallel conductors. Okay. Diagram of finding the force per unit length. Force per unit length between two straight parallel current carrying conductors. Suppose there are two conductors. This is conductor 1 and this is conductor 2. This is wire 1 and this is wire 2. Suppose the distance between the two wires is r, and let the two wires are placed. Let these two wires are placed in vacuum, or you can say in air, and the distance between them is r. Suppose this wire is carrying current I1 and this wire is carrying current I2. And you know that the current carrying wire can produce magnetic field. So when a wire carries current, magnetic field is produced around it in the form of concentric circles. So the magnetic field of this wire will be like this. If we hold this wire in our right hand like this, so magnetic field at this point, you can see this wire is placed in the magnetic field of this wire, and this wire is placed in the magnetic field of this wire. So both the wires are placed in the magnetic field of each other. So this wire is carrying current in this direction. So magnetic field lines will be like this. You can see. So magnetic field lines of this wire will be like this. So you can see that this wire 2 is placed in the magnetic field of wire 1. Similarly, we can have that wire 1 is placed in the magnetic field of wire 2. So both the wires are placed in the magnetic field of each other, and the magnetic field of this wire at this point will be inward. If we use right hand thumb rule, we can easily find out that magnetic field of this wire at this point will be inward, and it is V1. And because this wire is placed in the magnetic field of this wire, and so this wire will experience a force. You know, when a current carrying wire is placed in magnetic field, it experiences a force. So force of this wire, the current I2 due to the magnetic field of this wire will be in this direction. We can find out this force using Fleming's left hand rule. So this will be the force on wire 2 B is the magnetic field. The magnetic field of this wire at this point will be inward. Current in this wire is upward, and you can see that force will be towards left. Force on this wire will be towards left. Now you can find, similarly you can see that this wire, the wire 1, is placed in the magnetic field of wire 2. So the magnetic field of wire 2, if we hold this wire in our right hand like this, so at this point towards left, the magnetic field will be outward. At this point you can see that magnetic field will be outward. Suppose this magnetic field is B2. Now this wire is placed in the magnetic field of this wire, and the direction of force will be, you can see that. So first of all we will see magnetic field is this. This is the direction of magnetic field, and you can see this is the direction of current. So force on this wire will be towards right. Force will be towards right. राइट की तरफ फोर्स हो जाएगा. तो हम देखेंगे यहाँ पे ये जो फोर्स हो गया, force is towards right F12. So diagram is ready. Using this diagram you can find the force per unit length between two straight conductors which are carrying current. Okay, so now let us draw the another diagram which is very important from the example point of view. That is diagram to find the torque on a rectangular coil carrying current and placed in magnetic field. Okay. Torque on a rectangular coil. Torque on rectangular coil in magnetic field. So to draw this diagram, let us make a coil. Suppose this is a rectangular coil, and this rectangular coil, you can see that this rectangular coil, suppose it is placed in magnetic field. This coil is A, B, C, D. So first of all, you will draw this coil. Okay, then it is placed in magnetic field. You can draw magnetic field, uniform magnetic field, like this, and this. So this is the magnetic field in which this rectangular coil is placed, and you can draw the normals at this point of the coil. Now you can see that because this current carrying coil consists of 4 arms, it has 4 wires A, B, B, C, C, D and D, A. Now this coil is carrying current, suppose like this, in anti-clockwise direction. Once again, this coil is carrying current I. So because this coil is made up of 4 wires A, B, B, C, C, D and D, A. Now all these 4 wires are placed in the magnetic field, and we know that the current carrying wire placed in magnetic field experiences a force. So all the 4 wires A, B, B, C, C, D and D, A, they will experience a force. So force on this wire will be upward, that is FAD, and force on wire this will be downward, that will be FBC. And the force, if we use the rules to find the direction of force using Fleming's left hand rule, we can easily find these directions. And the direction on this wire, direction of the force on this wire will be upward, and direction of the force on this wire will be downward. And the force on this wire will be outward like this. This will be FAB, and the force on this wire will be inward, that is FCD. So these 2 wires, they experience equal and opposite force. So the FAD and FBC, these 2 forces being equal and opposite cancel out, and these 2 forces, you can see that FAB is outward direction and FCD is in inward direction, because these 2 forces are equal and opposite and acting along different lines of action. So they will constitute a torque, and due to this torque, this coil will start rotating. So this is the diagram to find the torque acting on a current carrying rectangular coil placed in magnetic field. You can easily find the torque acting on the rectangular coil, and during this you can say derivation, we have to find the perpendicular distance between these 2 forces, this force and this force. So to find the perpendicular distance between these 2 forces, we have to make a sub-diagram of this diagram. Sub-diagram, what you do, you draw this wire AD. Suppose this diagram is drawn to find the perpendicular distance AD, and this force FAB, which is acting in outward direction, we draw here FAB, and the force which is this one FCD, this we draw here like this. So you can see that the perpendicular distance between these two forces will be this one. So this is the perpendicular distance between two forces, that is ND. Right? Suppose the angle between current and magnetic field is theta. Suppose this is the angle and this angle is suppose theta, and if this angle is theta, this was the magnetic field, and if this angle is theta, so this will also be theta. And if this angle is theta, so you can find using this triangle easily find this perpendicular distance. If we take the length of this rectangular coil is L and the breadth of this rectangular coil we can take B. So if the breadth of this rectangular coil this is B and if this is B, you can easily find this perpendicular distance using this diagram. So this is the diagram to find the torque acting on a current carrying rectangular coil placed in magnetic field. Okay, so now let us draw another diagram that is the diagram of moving coil galvanometer. It's a very important topic which is frequently asked in the board exam, so please do practice it again and again. That is moving coil galvanometer. Sometimes we abbreviate and we call it MCG, moving coil galvanometer. Our next diagram is moving coil galvanometer. Okay, so let us start drawing the diagram of moving coil galvanometer. Moving coil galvanometer, that is MCG. So first of all we draw a torsion head. From there we suspend a wire which is made up of phosphor bronze, and there is a concave mirror. You can draw like this concave mirror. Now there is a rectangular coil which is wound over a non-metallic frame. Like this you can draw rectangular coil over a non-metallic frame. You can have so many turns of this coil like this. And finally there is a spring that is called a horsehair spring, and this is your diagram. Now this is the rectangular coil, and this rectangular coil is wound over a metallic cylindrical soft iron core. This is a soft iron core which is used to make the galvanometer dead heat and to increase the magnetic field. Now this rectangular coil is placed in magnetic field, and this magnetic field should be radial, and to make the radial magnetic field the pole pieces of magnet are made concave like this. So this is the concave pole pieces of magnet, you can see, and these concave pieces are drawn to have the radial magnetic field. Now the two ends of the galvanometer are, suppose this is the end 1, suppose this is terminal A of the galvanometer and this is the terminal B. Now to measure any current, if you want to measure any current using this galvanometer, you just pass current through this galvanometer. The current will start flowing through here, it will pass through the coil like this, it will come out from here. And because that this current carrying coil is placed in magnetic field, you can see this current carrying coil, this coil is placed in magnetic field of this north and south poles. This magnetic field is radial. So this coil, as we have already studied that a current carrying coil placed in magnetic field experiences a torque. So this coil will experience a torque and it will start rotating. And when this coil will start rotating, and if we can attach a needle to this coil, that needle will also rotate, and we can have a scale there, and that needle will move on the scale. So we can draw another diagram here to show that needle scale movement, how a needle moves. So we can show like this. Suppose this is the radial magnetic field, and if we show the top section of this galvanometer from here, if I show it like this, so you can draw the top section of this rectangular coil. It has so many turns, and a needle is pivoted here at the center. There is a needle and there is a scale like this. You can have a scale, and on this scale there is a 0 in between, and 1, 2, 3 on this side and 1, 2, 3 on this side. So this is the radial magnetic field. This is needle scale arrangement. In ancient galvanometers, we generally used this concave mirror, but now we use needle scale arrangement to take readings using the galvanometer. So this is the top section of this galvanometer coil, अगर इसको हम यहाँ से देखते हैं ऐसे करके, तो अगर ये यहाँ से ऐसे कॉइल है, तो यहाँ से अगर हम क्वेश्चन दिखा रहे हैं इसको, दिस सेक्शन इज शोन टू यू, यहाँ से इसको दिखा रहे हैं, और यहाँ पे वी कैन अटैच नीडल लाइक दिस, तो अगर नीडल हम अटैच करेंगे, व्हेन दिस कॉइल विल रोटेट, सो दिस कॉइल विल रोटेट, सो इफ वी कनेक्ट a needle like this you can show, if this coil will rotate like this, so the needle will rotate on the screen, ऐसे करके। तो ऐसे जब ये कॉइल घूमेगा, रोटेट करेगा, जब इसमें हम टॉर्क लगेगा, so coil will rotate, and if we connect a needle to the coil, this needle will rotate on the scale, and we can have the readings using the moving coil. So galvanometer, this is your diagram ready to find the, now you can show here your soft iron core also. There was a soft iron core that I have forgotten here. This soft iron core is used to make the magnetic field radial. Using this soft iron core, you can make a radial magnetic field like this. So this is moving coil galvanometer. So please practice, do practice again and again. It's a very important topic, and please see these videos again and again. Please like them and share them. Okay, thank you.